Thanks for the invitation. It's a pleasure to be talking to such a diverse crowd of K-theorists. So I hope you enjoy my talk. Today I will be talking on joint work with Patchkoria and Moi. And with Ogle. So the idea is to interpret all the objects that we know and like Hermitian K-theory or L-theory, via modern machinery, and more specifically through stable equivariant homotopy theory, and then get some mileage out of this higher structure. So I'm going to start with a very brief introduction on stable equivariant homotopy theory. And just in case you're not so familiar with this, you can hopefully just black box this introduction and at least work with the terminology I'm going to introduce. So G finite group, and for the purpose of this talk, I'm only going to talk about Z mod 2. And so what's the category of G spectra? Well, formally, it's what you get by taking pointed G spaces and formally invert the representation sphere, the regular representation sphere. And we are lucky enough that there are very nice point set models for this category. And my favorite, there are many, my favorite is just G objects in, let's say, orthogonal spectra. Okay? And one needs to be a bit careful on what the equivalences are. Somehow they need to involve representations of G, but at least the underlying categories can just be taken to be G objects in spectra. And this makes it very convenient to, it's actually particularly easy to build objects in this category, for example. If you care only about connective G spectra, you can just get away with gamma spaces even, functors from finite pointed sets to G spaces. Okay, and what are the features of this category? So we have functors. There are important functors. So from pointed G spaces, there is a suspension functor, suspension spectrum functor, to this category of G spectra that I'm going to denote like this. And the derived right adjoint for this functor is some infinite loop space functor. And then we have fixed point functors, particularly two kinds of fixed points. Derived fixed points, which we usually only call fixed points, and geometric fixed points. And these take a G spectrum and send it to a spectrum. And these have the feature that an age runs through the subgroups of G. And this has the feature that they define the equivalences on this category. So for example, so both families where age runs through subgroups of G, or this one, preserve and detect equivalences. Meaning if you have a map and you wonder, is this an equivalence of G spectra, you can just test if it's an equivalence on all the fixed points, or equivalently test if they're an equivalence on geometric fixed points. And how are these related? Now let's specialize this to G equals Z mod 2. How are these related? Well, there is a co-fiber sequence or fiber sequence. So if you take a Z mod 2 spectrum, you take the homotopy orbits, these maps to the fixed points, and these maps to geometric fixed points. Okay. So this gives you a relation between these two different types of fixed points. And moreover, and we're going to actually use this quite a bit, this splits away from 2. Okay, meaning that we get a decomposition if you take the fixed point spectrum and formally invert 2, this splits as the direct sum of the geometric fixed points, 2 inverted, and, well, the homotopy orbits be 2 inverted, but if you invert 2, that's equivalent to the homotopy fixed points. Now we need to be a bit careful. We need to make sure to invert 2 before we take homotopy fixed points. Okay. And we're actually going to use this formula later. So I'm going to box this. Okay. And I think this was the last thing I wanted to talk about. So this is my introduction to G-spectra. But hopefully this formalizer will get us far enough. Are there any questions? Okay. So next I'm going to talk about real algebraic K-theory. You can work this out in many generalities. Today we're going to use the sort of simplest possible one, and we just do group completion. This is going to be plenty for today's applications. Completion. So let me start with a formal construction. If you start, let's take G to be a topological let's say a topological group with an anti-involution. So what's an anti-involution is simply a group homomorphism from the opposite group to the group, meaning it's a map that switches around the multiplication in the group, it's unital, and it squares to the identity. So this and tau square is the identity. If you have this input, then this gives you a Zemo2 action on the bar construction of the group. Okay, and how is it defined? Well, at the simplicial level, it takes a string of elements in your group, and it sends it to, well, you want to just apply this involution component-wise, but because it switches the multiplication around, you're going to have to flip this whole sequence in order to preserve the simplicial structure. So this is defined by G1. And we denote the resulting Zemo2 space by B sigma G. Okay. And sigma is notation for the sign representation. If you think of BG as being configurations of points in the circle, we label in G. This is roughly taking configurations in the sign representation sphere. Is notation for the space BG with the specific Zemo2 action. Okay. So let's see some examples of this construction. It's going to be very handy. So first example is if tau is inversion, is a canonical anti-involution on any group, then if you take B sigma G, this is remember we can look at families of groups, of subgroups of a given group, and build a universal space. And now you can look at the subgroups of the group G cross Zemo2 with the property that the intersection with G is trivial. Okay, you can build a universal space. This is a space with an action of G cross Z2, and you can mod out the G action. Okay, and it is as a residual the Zemo2 action, and these are equivariantly equivalent. Okay, and this family of this is a family that comes up a lot in equivariant homotopy theory. So this is an example. In particular, you can see that if you take the fixed points, this splits as a wedge. disjoint union, I'm unpointed, over the elements of order 2 in the group of B of the centralizer. Okay. So this is an example. In general, if you take, so any tau, you get that these fixed points is the bar construction of, well, say two-sided bar construction on point, G and G acting on the fixed points, where the action of G on the fixed points is given by G times H is equal to G times H times tau G. Okay. This formula defines a left action of G on the fixed points, and you can take the bar construction of this action, and this is what the fixed points are. Okay. And finally, a last example, and this is going to be extremely relevant in a second for real K-theory. If you take a ring with anti-involution, so what is this? It's a map, sort of a similar structure. It's a map from the opposite ring to A, so it's a map, it's additive, but it switches the multiplication around, and it squares to the identity. So this is the standard input, for example, for L theory. Then you can look at GLN of this ring. This has an anti-involution. And how does that go? You take a matrix of entries in A, and you send it to the matrix. So you apply the involution entry-wise, and then you transpose. So it's going to be Ji. Now, from this example, we can define the real K-theory of a ring with anti-involution. And this definition, I mean, I want to define it as a Zemo 2 spectrum, and this is going to be a very special case of a construction of Hesselholt and Madsen, but I mean, in this generality, this is really, it comes out from a paper of Burgeli and Fedorovich. And here's the definition. The real K-theory of a ring with anti-involution, like that. What is it? You can take GLN of the ring with this anti-involution and take its B sigma. And then you take the disjoint union over N. And by block sum of matrices, this is a topological monoid with a Zemo 2 action. And you can take its group completion. Specifically, you just do loop of the bar construction of this topological monoid with Zemo 2 action. Okay, this is a space. And this, in fact, is the infinite loop space of a Z2 spectrum. And the way to do this, I think, for group completion, you can just get away with doing this in permutative categories. This is a category. Well, this is the classifying space of a category with a duality. And if you subdivide it and play around a little bit, you can turn that into a category with a Zemo 2 action. Zemo 2 action preserves the symmetric monoidal structure, and this is going to be the K-theory of that. So you can use one of the standard delooping machinery, or you can just write down a gamma space that deloops this thing. And, or if you want to be fancy, you can do a fancy as dot construction, but since the category is split exact, it's a bit of an overkill in this setup. Well, this is the Vrk Theory, I should say. It's the criteria of 3 modules. So I'm going to work with this definition. But yeah, if you want to be, you can probably change the pi naught or work with projective modules, but then you need to do something a bit different. It's a more complicated disjoint. I agree. For today, this is, I should probably say something. Vrk Theory. Okay, so this gives you a Azimuth spectrum, and now let's see what the fixed points are. So first of all, first is the underlying spectrum, and let me be a bit. So upper one means take the fixed point by the trivial group, which is just the underlying spectrum. This is equivalent to the K-theory of A. Again, I should say the Vrk theory, K-theory of 3 modules over A. And this is just by definition. Look at this thing, you just forget the Z2 action, and you get the group completion of the category of 3 modules. More interesting is what happens when you take the fixed point spectrum. And let me do this at the space level. This infinite loop space, I mean, the d-looping is right down. This is already this has the homotopy type of the infinite loop space already equivariantly, so the fixed point spectrum, at least the infinite loop space, has the homotopy type of the fixed points of this space. So let me just work this out at the space level. What happens if you take fixed points? Fixed points commute with loops and with the bar construction, and with this disjoint union. So you're going to get loop B of disjoint union over n of the fixed points of B sigma, but here we have them, is this one-sided bar construction. So we get B of point GLN acting on the fixed points under block sum. What is a fixed point? Is an invertible matrix, which is, I don't know if the right word is antisymmetric, maybe. The diagonal elements are going to be fixed by the anti-involution, and the upper half matrix is going to be determined by the lower half, up to applying the anti-involution omega, just by analyzing this formula. So this is actually, a fixed point here is exactly the datum of a Hermitian form over a 3A module. And now if you think a little bit about how the bar construction goes, you can find that this is actually isomorphic to the group completion of the category of Hermitian forms, and I should say over 3A modules. Okay, and this is really Burgelian-Fedorovich. Okay, so we sort of bundled up K-theory and Hermitian K-theory into one object, and now I want to.
You said this is already the derived fixed points?
Yes, this is already the derived fixed point. So it works like in K-theory. This is as a gamma space, this is special, and this is, this is loop of the first space of the gamma space, and from then on, all the structure maps are equivalences.
But where, shouldn't there be Z12?
Yeah. You can deloop by representations, and the theorem is that this is already, is a positively fibrant in the Z2 sense. It means if you look at the value of the spectrum at any representation which contains at least a copy of the trivial representation, you get from then on, all the structure maps are equivalences. Yeah. And so you just need to look at the trivial representation. Other questions? So we know what the underlying spectrum is, what the fixed points are. How about the geometric fixed points? And this is again essentially Burgelian-Fedorovich. And this result has been improved a little bit by Bruce Williams and by Schlichting. And if you look at the geometric fixed points of KR, actually, maybe let me do it like this. If you look at the Hermitian K-theory of A, by this remark, this is the fixed points. If you invert 2, remember, is it still around somewhere up there, the boxed formula, this splits as, let me take homotopy groups to be safe. So you get a splitting on the right-hand side as the geometric fixed points of real K-theory. with 2 inverted, and the homotopy groups of the homotopy fixed points. But if you invert 2, this can actually be computed from the homotopy group of K-theory and the residual Azimuth 2 action. And I need to invert 2 as well. 1/2. Okay. This is a formal splitting that you get for every Azimuth 2 spectrum, you get this splitting. And what Burgeli and Fedorovich show is that this also splits as L theory of A. 1/2. And a copy of the same spectrum. And now you can wonder, well, does this identify this and this? And the answer is yes. So in fact, you can deduce from this, you can just calculate the composite and see it's the diagonal, it's a block sum of 2 maps. And so this identifies this guy and this guy. This is really messy, but so let me write it like this. The upshot is that if you take the L theory of A and invert 2, this is equivalent to the geometric fixed points of Vrk theory. Okay. So up to inverting 2, L theory is also bounded up in this object. Okay. Now we're going to get some mileage out of this fact, but first, I want to extend this to ring spectra. And we're going to see later why that's relevant. I'm just going to state this as a theorem. And somehow the idea is to copy the formula over there. So again, up to pi naught, K-theory of a ring spectrum can be defined by the same formula, essentially, just where you need to be a bit careful what you mean by GLN. And now, the idea is to define, again, the same involution on GLN by transposition, and entry-wise applying the anti-involution. The problem is that that's actually harder than it sounds, but that's only technical. And if you can pull that off, then you can extend your functor, I made a mess, to ring spectra. So let me state this as a theorem. Is that the functor KR extends as follows. You have rings with anti-involution. And this functor KR to Z2 spectra. And here there is another category of ring spectra with anti-involution. And there is an Eilenberg-MacLean functor this way, and the claim is that this functor extends like this. Okay, now we need to really be careful about what we mean by this. In Poinsett land, an object in here is just a ring spectrum. It has a strict Azimuth 2 action, and the Azimuth 2 action defines a map from the opposite ring spectrum to the ring spectrum. So I'm going to call this functor KR again. A note of warning, how homotopical is this functor? And the answer is that KR preserves equivalences of underlying Azimuth 2 spectra. So in this Poinsett model, a ring spectrum with anti-involution has an underlying genuine Z2 spectrum, and this KR functor is going to preserve genuine equivalences. This is actually not so surprising. So Burgeli and Fedorovich have an intermediate extension to simplicial rings with anti-involution, and their construction also preserves maps of simplicial rings which are equivalences of underlying Zemo2 spaces. So this is actually fits into the framework quite well. That's sort of reasonable. So in particular, well,
So wait, you put that as a warning, it's not good?
I would say so, but some people would complain. Burgeli and Fedorovich work really hard to show that if after they invert 2, their functor on simplicial ring actually depends only on the underlying homotopy type. I like to work with equivariant equivalence, so I'm really happy about this. But somehow, yeah, I'm happy about that. So in particular, yeah, there are other people that have setups for real K-theory where their input does not have a genuine equivalent homotopy type. It's some sort of ring with a homotopy coherent only, Zemo2 action. And their functor preserves only, the only equivalence you can have, equivalence of underlying spectra. This is sort of a refinement of that construction. You can forget the sort of fixed point information. I see. So you should think of this as a refinement. For example, Spitzbach has a functor like this, where he just looks at homotopy coherent actions, and this is essentially a refinement of that functor that takes into account the genuine equivalent homotopy type. Okay, so fine. We have this extension. Now, what we want to do is we want to study real K-theory, just because it contains so much information about things we care about. And how do we do this? Well, the idea. There's a standard method to study K-theory, which is trace maps. So, what's the basic philosophy? If you have a natural transformation from K-theory to THH, is useful. Maybe so is. So is some sort of trace from real K-theory to some real version of topological Hochschild homology. And now I'm going to talk about this. So section 1 is real THH, and this is joint work with Moi and Patchkoria. So what is the idea of THH? That's just a recall. If A is a ring spectrum, and let's say that it's flat, then this is equivalent to the cyclic we saw this morning in Mike Mandel's talk. You can form let me just write this, the cyclic bar construction of A with respect to the smash product, and you could take this as a definition of THH. If A is not flat, you need to derive the smash product, and Böckstedt has a definition which sort of incorporates this derived smash. So in general, we think of this as an equivalence. Although, nowadays you can just flat replace and then work with that. Okay, so now we want to do something similar. If the input is an anti-involution. So let's say if A has, actually, maybe let me say something more. Another way of thinking of this is you can take A, so A is an AA bimodule, and so you can look at this as a module over A smash A up, the enveloping algebra, and well, one on the left, one on the right. And in fact, if you take the derived smash product, this is what models this construction. Okay, so I want to do something similar for ring spectra with anti-involution. So if A has an anti-involution, what do we get? Well, it's like this. So we get a Zemo2 action on the cyclic nerve. So let me remind you what the cyclic nerve is. The cyclic nerve is the geometric realization of a simplicial spectrum, which in degree n is A smash with A n copies of A. And this anti-involution is going to apply, let me write down a formula, which is, in quotes. You take a tuple of elements like this, and you send it to, you want to apply the anti-involution entry-wise, but then because of this op, you need to be careful about the simplicial structure. And if you think a little bit about how the simplicial structure is defined, this formula is going to behave well with the simplicial structure. And this is the Dahiro. It's known as the Dahiro bar construction. And so the theorem is what we do. We give a sort of homotopical interpretation of A. We should say. So this construction can be formalized by looking at this as an indexed mesh product. So this indexed mesh product. As in defined by Hill-Hopkins-Ravenel for orthogonal Z2 spectra. And the theorem is that the real topological Hochschild homology can be modeled by this object, the dihedral nerve of A, if again A is flat. And again, I mentioned before that we sort of, this construction have to do with the underlying equivariant homotopy type. So I'm going to ask it to be flat as a Z2 spectrum. So the underlying Z2 spectrum of A is flat. Then the real topological Hochschild homology can be modeled by the dihedral bar construction, and this can be actually interpreted by, let me just do this quickly. I don't have to explain too much, but you can take your ring with anti-involution, forget the anti-involution, and then take the norm construction. This is sort of a multiplicative induction from ring spectra to Z2 ring spectra, and the underlying ring spectrum is just the enveloping algebra. And you can use the anti-involution to build a left and right modular structure over this Z2 spectrum and take the derived mesh product in there. So it can be modeled like that. And in particular, we get a good handle on the geometric fixed points of this thing. There is a left and right modular structure of A acting on the geometric fixed points, and the geometric fixed points of THR can be modeled by the derived mesh product of A as A modules. So in particular, this allows us to calculate this object fairly well. The actual fixed points are tricky, and the problem is that it's hard to calculate the fixed points of this indexed mesh product. But at least we get a handle on the geometric fixed points, and then you can play around with the isotropy separation and try to get information about fixed points like that. And again, I mean, I write THR is equivalent to that because there is sort of, if your ring is not flat, there is another construction, which is essentially a Z2 equivalent version of Böckstedt's original construction of THH, which has cofibrant replacement sort of built in. And what we do is that we compare that construction with the dihedral bar construction in the case where your input is already cofibrant or flat. Okay. Let's see. Right. So, what is the point of the theorem is that we can start calculating things. So, here's some calculations. And these are fairly new, and we are trying really to understand this object well, but here's some of them. So first, Huygens shows that if you take the real topological Hochschild homology of, you can take the sphere spectrum and smash it with a topological group, probably well pointed, and this is a ring spectrum just by multiplication in the group, and you can look at the anti-involution coming from the inversion in G and trivial on the sphere. And this is equivalent to the equivariant suspension spectrum of the free loop space on BG with the right involution. So we take our favorite B sigma here that we defined at the beginning, and then the free loop space is with respect to the sign representation. So here, lambda sigma means maps, unpointed maps, out of the one point compactification of the representation of the sign representation. Okay. So this is a model for the free loop space. And this, in fact, can be extended to any coefficients. If you take THR of, you start with a ring spectrum with anti-involution, and you do this group algebra construction, then this splits as the real THH of the coefficients, and again the same. I'm missing a base point. The same free loop space. We have, and this is not too bad. This is sort of what THH is built to model, is exactly the free loop space. So this is sort of expected. You have other calculations that are a bit more complicated. Is if you take real THH of Fp, by which I mean take Fp with a trivial involution, like this. Trivial involution on the input doesn't mean trivial involution on the output. Think of Hermitian K-theory, for example. If you take Hermitian K-theory of Z with a trivial involution, you get something interesting out of it. This splits as a wedge of Eilenberg-MacLane spectra. Oops, suspensions. N times the regular representation, suspend by that. And HFP, by which I mean the constant Mackey functor defined by Fp, or you can take the standard Eilenberg-MacLane construction on Fp with the trivial Z02 action, and you get a Z02 spectrum, and the fixed points of that are actually interesting. And for this we can calculate everything. So from this we can calculate both the fixed points. So this is actually, maybe let me say like this. This is the free HFP algebra on the regular representation sphere. And this we can calculate the homotopy groups of the fixed points. And, well, let me say, as well as the bigraded. So if you have a spectrum, you can always take the bigraded homotopy groups as Z2 spectrum, and we can calculate that too. So, yeah. Yeah, yeah. Regular representation.
So what kind of methods go into these calculations?
Yeah, so this one Christian found a very clever way to reduce it to Böckstedt calculation. So essentially, we know that the underlying homotopy type is right. By that geometric fixed point formula, we know that the geometric fixed points agree. We could just need to know what the geometric fixed points on this side are. And then it just boils down to writing a map that implements that equivalence. And you essentially go through Böckstedt construction of this map and make it work equivariantly. And then in order to identify that the maps does the right thing on geometric fixed points, you play around with isotropy separation a lot, and you actually get it. So, by the way, if P is odd, the geometric fixed points here are trivial. and so are they on this side, because in FP2 is invertible and there are no geometric fixed points if you invert 2. So it's actually, as soon as you have a map that is the right map on the underlying, you get this equivariant equivalence if P is odd, and for P equal 2 you need to work more. But that's how we get it.
Just for finite prime fields or for any finite field?
No, this is only for FP. Yeah. Yeah. So what is fairly easy is that this is a free FP algebra, so it's easy to build a maps out of free things. We're trying to do the same thing for Z, and this is much harder. So we think that this should be HZ, wedge, a bunch of suspension again, now with a shift. Let me get this right. So this is the right underlying homotopy type, and we can calculate the geometric fixed points agree as well. Now it's hard to build a map because this thing is not free anymore as a Z algebra, so we don't know what to do. But at least at odd primes, so P locally, P odd, we get that this is Z modulo P. P to the P exponent in the prime decomposition of n. Okay. So this we can prove. For P equal 2, we don't know. Yeah. And this we do. And finally, actually maybe I should have started with this one. There's a really nice calculation. Is that what happens in pi naught? If A is connective, pi naught of A is equivalent to, sorry, pi naught of, what am I talking about? Pi naught of real THH of A, Z mod 2. This is equivalent to pi naught of the fixed points, tensor pi naught of the fixed points, modulo some Witt relations which come from a certain action of a non-commutative version of the two truncated Witt vectors on this group. And we can calculate the full Mackey functor structure on this in terms of a module structure of the Mackey functor pi naught of A, module structure over this a certain Witt vector Mackey functor object. And if A, to give you an idea what these relations are, if A is commutative, these are of the form, if you take the transfer y tensor x, you can move the transfer on the other side. And similarly for, if A is commutative, you have a norm, and the same goes for the norm. And in the non-commutative case, they're a bit more complicated. At least in some sense, they come from pi naught of the enveloping algebra up here. Okay. So this is what I wanted to say about THH. And now how about the relation with Vrk K-theory? So I'll talk about the trace map. So theorem. Joint with Ogle, we build a trace. We don't quite hit the bar construction, we hit the other model for THH, so put together with this comparison result, we get that there is a natural transformation from the real K-theory to real THH was underlying map. Is the standard trace map of Böckstedt. So there is this natural transformation, and in particular, we get, if you take fixed points, I mean, for A discrete, meaning if A is just a ring with anti-involution, we get a map from the fixed points of K-theory, which is the Hermitian K-theory, to the fixed points of THH. And, well, we get a map from the geometric fixed points of real K-theory to the geometric fixed points THH. Now this we calculated here is this mesh product derived. Okay, and over here, if you invert 2, remember this was L theory. So we get a natural transformation from L theory to something after inverting 2. But if you invert 2 on this side, you get 0. So we built a natural transformation from L theory to 0. And this is actually not too surprising. So there is work of Cortinas and Lauder that they built a Chern character from rational Hermitian K-theory to rational dihedral homology. And they also show that if you restrict it to the L theory summand, you get 0. And this essentially justifies this result in the sense that, well, everything, it comes from a positive spectra. There is a splitting coming from isotropy separation after you invert 2. And of course, you know, the geometric fixed point summand maps to the geometric fixed point summand, and the whole summand is 0. Okay, so this is, you know, at first sight disappointing, but this happens only for discrete rings. Okay. So in particular, if A is not discrete, geometric fixed points can be very interesting. And in fact, we have a little longer. I'm going to talk about how you can, if instead of working over the integers, you work over the sphere, you get interesting invariants. And somehow, if you want to know about all the objects, you need to pay a price, and you need to know how to come back to the sphere, to the integers from the sphere. And, well, that you need to work for. So maybe, so let me start by, you know, giving you a little taste of how, you know, to show you that at least in some cases the trace is interesting, even on fixed points. Because so far I only showed you 0. So here's the theorem. So let's see. So there is an assembly that goes from the suspension path spectrum of PG, actually call it pi, into the real K-theory of the spherical group ring. Oh, sorry, important. B sigma, where again, the anti-involution on pi is given by inversion, and which is split. A split mono. And it's split by a map defined from the trace. So we can take real K-theory of the spherical group ring, take the trace to the real topological Hochschild homology. And now remember there was this calculation of Hugenhill that shows that this is the suspension spectrum of the free loop space on this space B sigma, and you can take the evaluation map at the fixed point of the circle, and you get. Did I switch my G's to pi? Yeah, sorry, these are pi's. Okay, this defines the retraction for that map. So we get a splitting as the suspension spectrum of this Z2 space wedge something that you want to call the wider spectrum maybe, but it would be really interesting to analyze the so first of all, the underlying spectrum is the wider spectrum, and this is related to stable H cobordisms. Now what that thing is, what the fixed points of that are, I have no idea, but that would be nice to understand. Okay, and then if you take fixed points and geometric fixed points, you get analogous splittings for what you want to call the Hermitian K-theory or the L theory of the spherical group ring. So, and this is only for the sphere. This is sort of a new object, we define a splitting, but now let me tell you about objects we know. So, so there is an application to the Novikov conjecture. So let me remind you what the Novikov conjecture say. For a discrete group phi, it says that the assembly map in L theory is rational. It's rationally injective. Okay, and this has been verified in for a lot of groups, always by geometric methods, and as far as I know, there's no general homotopy theoretical strategy to attack this problem. And I'm going to suggest such a strategy using the trace as follows. It's a theorem. Is that there is a diagram. So you can restrict this assembly along the unit map. So this is a ring spectrum. You can take the unit map in. This gives you a map from the suspension of V pi into the spherical group, into the L theory of the group ring. So this is let's call this alpha, and let's call this alpha 0. So this sort of is restricted assembly. Remember, after inverting 2, this is the geometric fixed points of K-theory. And there's a map down. Let's see, yes. Now I'm going to replace. I'm going to replace the integers for the sphere, and there's a map like this. And in fact, the assembly I defined earlier provides me with an assembly like this. And essentially, this composite gives a splitting. That I'm going to call evaluation composed with trace. So what happens is that so let's just stare at this thing. Rationalize everything, it turns out that this is injective if and only if this map here, and this splitting, is 0 on the kernel of this map. You can think about it a little bit. I'm going to call it H for Hurewicz map, so we trade the sphere for Z. So as we get a corollary for this theorem. Now, this is only for the restricted assembly. It turns out that if this retraction descends, it descends to a natural transformation because the trace is natural. And if you play around with periodicity, you can get from the injectivity of this piece of the assembly to the whole injectivity. So the corollary we get is that yes, so this is very small. Rationally, that's just the rational homology of B pi. Absolutely. Absolutely. This map, we do not expect this to be a rational equivalence. The point is that, as I mentioned before, real K-theory depends on the equivariant homotopy type of the sphere. The sphere and Z are rationally equivalent only non-equivariantly. Equivariantly, the sphere is rationally equivalent to the Burnside-Mackey functor, and this is bigger than Z. So there's no chance this is an equivalence. Maybe. So let's wrap this up. So Novikov holds for pi if and only if this map evaluation composed with trace is rationally 0. On the kernel of H, rationalized. So now, last minute, the question is, how do you understand the kernel of that map, of the map H? And, well, this is tricky. So you can easily see that that condition on being 0 on the kernel is equivalent to, well, is going to give you a natural splitting of this map. Think about it. Well, this is 0 on the kernel of this. It means that it descends to a map here.
My problem is that
It's alpha 0. Alpha 0 is the restriction of alpha along the unit. Okay. And the point is that rationally, the L-theory of Z is a bunch of shifted copies of Z by periodicity in every fourth degree. And, well, you have to work a bit to show that injectivity of this piece gives you injectivity of the whole thing. Essentially, you take a polynomial in here, but using periodicity you can shift it so that the leading coefficient lies in degree 0. And what you do, you send it around here and then back. The leading coefficient is going to be sent to something non-zero because of this splitting. And then you need to make sure that the other terms do not cancel that term. And it's a naturality argument because everything comes from a higher dimension in the rational homology of B pi. Using naturality of the trace, you can show that all the other terms go to 0. I'd be happy to go through it. So maybe, okay, I'm out of time, so let me just be brief. Hope is to understand. So the kernel of H rationally, non-equivariantly, this is equivalent to negative sigma homology by this theorem of Goodwillie. So we hope, and so the equivalence is given by the trace. So we hope to understand this kernel in terms of the homotopy fixed points of real THH and then homotopy. Okay. And if we can do this, in fact, this map factors through this guy. So if you can show that the map we are hoping to show that the map from here to the rational homology of B pi is 0, at least on the kernel of H. And there are spectral sequences that complete this thing, but it's complicated, and especially showing that a map out of a, it's hard to use spectral sequences to show the maps are 0. So I don't think this is going to be easy, but at least you have a strategy. Okay, I'm going to stop here.
Questions?
So how is this related to Mathias' real K-theory?
Yeah. So, well, up to topology on complex numbers or not?
Well, for example, if you take BU
Yes.
as an equivariant spectrum that represents Mathias' real K-theory.
Yes. So you can do a similar group completion construction. You can use, there is a subtlety. How do you act on BU? So let's see. Let's think about this for a second. At TSK theory, you act on BU by entry-wise conjugation. There's no transposition, but because you're on BU, entry-wise conjugation corresponds to transposition and inversion. And so a TS construction has to do with involutions. This has to do with anti-involutions. The way you turn an anti-involution to an involution is composing via inversion, and that gives you the vocabulary between the two constructions. So, and because you're working on the unitary group, transposition corresponds to entry-wise conjugation under inversion. So these are going to give you the same, they're going to be equivalent if you topologize the complex numbers.
Now you're just talking about the complex numbers. If I take
Yes.
G space, the space with an involution,
So then you
it
can
gives you something.
you can look at the category of vector bundles over the space.
How does this fit with what you're doing?
So then you need to talk about categories with duality. But you can, so you need to be a bit more careful than just group completion. But Hesselholt and Madsen have a version of the S-dot construction that works for categories with duality, for exact categories with duality, and that gives you a TSKR.
You do continuous functions or
Yes.
things as a ring and put involutions back.
Well, he's
Yes.
giving you a Z2 spectrum, and if he doesn't get a Z2 spectrum, he just gets a spectrum.
No, it gets the Z2 spectrum.
The Z2 spectrum represents KR.
Yes.
If you take a map of two Z-mod 2 spectra, you get a spectrum.
Do you have a geometric candidate for this y spectrum?
No, no idea. No. I mean, it's a lot of work. You need to go through the whole Feldhausen, Jaren, Ragnes, and yeah, I don't know. We're just trying to sort out what the involution should be. I mean, with Christoph, and even understanding which involution on K, if this is the right involution on K-theory, that corresponds to anything geometric, even without talking about fixed point spectra, just the involution it's a mess. It's not clear.